In this video, we are going to look into concept of aromaticity and what makes particular molecule or ion aromatic. Earlier in our analysis of compounds with delocalized electrons, we have seen that species is aromatic if it is unsaturated, which means has carbon-carbon double bonds. If it is conjugated, that means that double bonds are conjugated to each other. So each double bond is separated from the next one by a single bond. It has to be also planar, which means that ring is flat. That's in general requirement for electron delocalization anyway. And finally, the molecule or ion had to be cyclic. So conjugated double bonds had to form a ring. And of course, an example that satisfied all these requirements was molecule of benzene. So on the left, molecule of benzene is shown as molecular orbital representation. So 6 atomic p orbitals on carbon overlap to give molecular pi orbitals of benzene, and one of the delocalized pi orbitals of benzene is shown here. Or on the right, we have valence bond representation of electron delocalization in benzene, shown as 2 resonance structures of benzene molecule. Ever since the discovery of benzene and identification of its unique properties, its unusually high stability, there was question whether similar compounds are also aromatic, whether they will also exhibit similar properties. So in the 19th century and ever since, the goal of chemists was to prepare compounds such as cyclobutadiene, specifically 1,3-cyclobutadiene, and cyclooctatetraene, again specifically 1,3,5,7-cyclooctatetraene, and then examine their properties, whether they are aromatic just like benzene. It turns out that they are not. Cyclobutadiene is an unstable molecule and couldn't be prepared. Eventually, it was prepared after Second World War. It was prepared only as highly unstable intermediate that could be kept in argon matrix. That means it could be only stored frozen in solid argon so that molecules cannot move and react. That's about as unstable as a species can get. Cyclooctatetraene was prepared much earlier, sometime around the beginning of 20th century, but it turned out that its properties were that of ordinary alkene, ordinary polyunsaturated alkene, and they were not aromatic in any way. And still, according to valence bond theory, we can draw 2 resonance structures for each of those species, cyclobutadiene, benzene, cyclooctatetraene. So according to valence bond theory, all of them should be equally stable. Difference in stability was explained by Hückel by application of molecular orbital theory. So in this case, only molecular orbital theory can explain properties of these molecules. So according to Hückel, for a species, molecular ion, to be aromatic, it has to be, as we have already seen, unsaturated, conjugated, planar, and cyclic. But in addition, there is one more requirement. A molecule must have 4n+2 conjugated electrons to be aromatic. If it doesn't, then not only that it's not aromatic, but it is actually anti-aromatic, and electron delocalization destabilizes it. In his study of molecules and ions with delocalized electrons, Hückel identified the concept of anti-aromaticity. It means that some molecules or ions are actually destabilized by electron delocalization. Up until then, it was believed that electron delocalization always results in stabilization of molecule or an ion. Hückel was the first one to identify that it was not the case, that in some rare instances electron delocalization could actually destabilize the system. One example is cyclopentadienyl cation. According to valence bond theory, we can draw 5 equivalent resonance structures, and we would expect that this compound would be stabilized by electron delocalization, and it actually should be easy to prepare. In fact, cyclopentadienyl cation is extremely unstable, cannot be prepared, and is one of the species that Hückel has identified as anti-aromatic. And that's because it does not satisfy its requirement that number of conjugated electrons in a ring have to be 4n plus 2, where n is a whole number. We can see that there are only 4 conjugated electrons in a ring. So this species is actually destabilized by electron delocalization. To explain concepts of aromaticity and anti-aromaticity, we have to apply molecular orbital theory. Clearly, valence bond theory is not satisfactory. So, to consider first molecular orbitals of ring system with delocalized electrons, we need to know where are relative energy levels. There is useful mnemonic to determine relative energy levels of those orbitals. What we should do is draw a polygon that has same number of corners as there are number of atoms in a ring. So for benzene, 6 carbons, so we draw a hexagon. And then we represent that hexagon with one corner pointing down. So energy levels of orbitals will be at each of the corners. In benzene, those orbitals are designated from psi 1 to psi 6. Energy level of 0 of starting atomic orbitals is exactly halfway through the energies of these orbitals as shown. So psi 1 to psi 3 are bonding and psi 4 to psi 6 anti-bonding. We can see that psi 2 and psi 3 are degenerate, same energy, among the bonding orbitals, and psi 4 and psi 5 also degenerate among the anti-bonding. Orbitals are of course filled up following Aufbau principle, from lowest energy level to the highest. Since benzene has 6 carbons and each carbon contributes 1 electron to its pi orbitals, there are a total of 6 pi electrons. We place them from lowest energy up, so we can see that all the bonding orbitals are filled up, all of the electrons are paired up, and all of the anti-bonding orbitals are empty. That's the best situation for any molecule like this. So this is extremely stable molecule. And also gap between HOMO and LUMO is relatively large, much larger compared to other compounds with unsaturated electrons. That makes benzene even more stable and even less reactive. So bond order is 3. I hope by now you know how to calculate bond order. So maximum bond order and maximum stability for a molecule like this. Now we consider molecules that are possibly anti-aromatic. We can see a little bit different situation. Let's consider cyclobutadiene. If we apply the same analysis, we should draw a square with one corner pointing down. That gives us energy levels of molecular pi orbitals. We can see that there is one bonding orbital, psi 1. Now psi 2 and psi 3 are degenerate, and they are right in the middle. They are right at the level of the original atomic p orbitals. That means they are non-bonding. And there are 4 pi electrons. Each carbon of cyclobutadiene contributes 1 p electron to form molecular pi bonds, so 4 pi electrons. We will again distribute them following Aufbau principle, that means in the lowest energy orbital first. But then we also have to apply other principles, such as Hund's rule of maximum multiplicity, which means that when orbitals are degenerate as psi 2 and psi 3, then electrons fit 1 per orbital first. Since we have only 2 electrons left, psi 2 and psi 3 have only 1 electron each. And that's it. We have distributed all the electrons. Now when we consider cyclobutadiene, we can see why it is anti-aromatic. According to molecular orbital theory, it's not even a stable molecule. It is a diradical. It is a species with unpaired electrons. So anti-aromatic species, as a result of electron delocalization, ends up with unpaired electrons. That's extremely unstable. That's actually a reaction intermediate. That's not a stable molecule. And following a valence bond representation, then if we look at molecular orbital description, then valence bond representation would be better by representing cyclobutadiene as biradical. So typical common representation shown on the top actually not quite correct. More accurate would be bottom one, that shows cyclopentadiene having one double bond and having two unpaired electrons, one on each carbon. If we consider next species ion cyclopentadienyl cation, we can see why it is unstable and why it is anti-aromatic. When we draw a pentagon to identify relative energy levels of its molecular orbitals, we can see that there are 3 bonding and 2 anti-bonding molecular pi orbitals. In this case, energy level 0, you can see, is drawn a little bit asymmetrically because we have odd number of pi bonds. So 3 bonding, 2 anti-bonding. Those 2 in terms of energy are as anti-bonding as these 3 are bonding. And again, we have only 4 valence electrons, 4 bonding electrons or pi electrons. That's because in case of cyclopentadienyl cation, we start with a total of 5 electrons, 1 from each carbon, and then we subtract 1 electron because this is cation, so it has lost 1 electron. So there are 4 electrons left, and they are left to be distributed in the existing molecular pi orbitals. Again, if we distribute them following Aufbau principle and Hans' rule of maximum multiplicity, we can see that lowest energy orbital psi1 is filled, while psi2 and psi3 degenerate molecular orbitals get 1 electron each. So again, just like cyclopentadienyl cation is unstable because it is a diradical. Then next, when we move on to cyclopentadienyl anion, we can see that's a very stable species, because following the same analysis, anion has 6 pi electrons, 5 original pi electrons, 1 from each carbon, and because it is anion, it has gained 1 additional electron, so there are a total of 6. With 6 pi electrons, then all of the bonding orbitals, psi1 to psi3, are filled. All anti-bonding are empty. So just like benzene, this is the best case scenario. There is maximum bond order, all the bonding orbitals are filled, all anti-bonding are empty, so that's very stable species. So cyclopentadienyl anion, according to molecular orbital theory, is going to be something that is very easy to prepare and is very stable. And that's indeed the case. Starting with cyclopentadiene, even treatment with relatively weak base for organic purposes, like hydroxide, will deprotonate it to give stable cyclopentadienyl anion. So these observations, our inability to prepare cyclopentadienyl cation or cyclopentadiene, and very easy preparation of cyclopentadienyl anion support molecular orbital view of antiaromaticity and aromaticity. Here we have a valence bond description of preparation of cyclopentadienyl anion. So we start with cyclopentadiene. Deprotonation readily occurs to give cyclopentadienyl anion. Cyclopentadienyl anion is stabilized through resonance, so 5 equivalent resonance structures, and the localization of negative charge over the 5 carbon atoms of the ring, and another representation. So that's valence bond theory, but as we have just seen, it's really molecular orbital theory that we should apply. Cyclooctatetraene shown here is not anti-aromatic. Anti-aromatic species are relatively rare. Only very small molecules, those that are so small that have to be planar, are anti-aromatic. Any molecule that is a bit larger will twist out of the plane to prevent electron delocalization and to avoid being anti-aromatic. So a molecule like cyclooctatetraene twists out of the plane and has Packard conformation. In fact, you may recognize it. It's a boat conformation. So cyclooctatetraene is in a boat conformation, and double bonds behave as isolated double bonds, at least the first approximation. So it is an ordinary alkene. It's not anti-aromatic. So keep that in mind. Only very small rings, 3, 4, 5-membered rings that have to be planar, could be anti-aromatic. A larger ring, like 8-membered ring, cannot be anti-aromatic because it will always twist out of planarity. In this case, the ring is in both conformation. There is not much difference in stability between both and chair conformations because there is only 1 proton, 1 hydrogen on each carbon. So there is no steric hindrance among those hydrogens, unlike cyclohexane where we have 2 hydrogens on each carbon. And also in this case, 2 double bonds that point up could interact to an extent. There could be some interaction, stabilizing interaction between them that slightly stabilizes both conformation. Here are some examples of aromatic hydrocarbons and how to identify them. If we start with example on the left, 10 carbon atoms, and there are 5 alternating double bonds in the ring. This compound is known as 10-annuline. We can see that it satisfies Hückel rule for being aromatic, so 4n plus 2 equals 10. There are 10 pi electrons, 5 double bonds, so it satisfies the equation for n equals 2. So it's aromatic. There are two different 14-annulines. We can refer to them as angular, one on the left, and linear, one on the right. 4n plus 2 equals 14, 7 double bonds, so 14 pi electrons. So that satisfies Hückel rule for n equals 3. And then 18-annuline, again, if you do the calculation, it satisfies Hückel rule for n equals 4. As these annulines get larger and larger, they actually tend to twist more and more out of planarity. And so even though theoretically they are aromatic, they actually tend to be less and less aromatic. Fused rings also could be aromatic, so naphthalene, of course, is aromatic. You can see it resembles 10-annuline. There's just an additional sigma bond that splits ring into 2 rings. Again, it satisfies Hückel rule for closed ring of 4n plus 2 pi electrons, where n is 2. So fused rings, again, we are considering only closed loop of pi electrons. Azulene is another variation, again, 10 carbons, 5 double bonds. It's just that rings are now 7 and 5 membered rings. So fused rings are 7 and 5 membered rings. Again, another aromatic species. Now be very careful in identifying closed loop of pi electrons, the localized pi electrons. Students would often make a mistake on a question like this, whether this is aromatic or not, because they would count all the double bonds and pi electrons, and they would count with 12 pi electrons because there are 6 double bonds. But actually it's only 5 double bonds that form closed loop of pi electrons, and they are here in this dashed box. 1 pi bond is outside the ring, and even though it's a part of another ring, that ring also contains an sp3 hybridized carbon, and you know that rings with sp3 hybridized carbon are not delocalized. So that double bond does not participate in electron delocalization, so it doesn't count. So this system is aromatic. There are only 5 delocalized double bonds in a ring, and so 4n plus 2 equals 10, n equals 2, that's aromatic system. Yet another system with 4 fused rings. Again, it is aromatic. There are 18 delocalized pi electrons, so aromatic system. And here is a molecule of anthracene. Well, on the left is actually phenanthrene, and on the right anthracene. Again, you can see they resemble 14 annulines. It's just that now we have fused rings, so additional bonds that split this large 14 annuline ring into individual fused rings. But number of pi electrons is the same, 14, and each species is aromatic. Of course, as we have seen already, ions could also be aromatic. But for an ion to be aromatic, we need to have carbon atom or carbon atoms of the ring that are sp2 hybridized. That means they either have to be carbocations with empty p orbital, atomic p orbital, or carbanions where free electron pair is in unhybridized p orbital. So examples are cyclopropenyl cation, and you can see that one is aromatic for n equals 0. So besides being whole number, n could also be 0 to satisfy Hückel requirement. So for n plus 2 also works if n is 0. Cyclopentadienyl anion, we have already seen that several times, and so that's also aromatic species. Another aromatic species that is very interesting is cycloheptatrianyl cation. Cycloheptatrianyl cation is aromatic, of course, because 4n plus 2 equals 6, 3 double bonds, and empty orbital on sp2 hybridized cationic carbon. This species is so stable that actually corresponding bromide, cycloheptatrianyl bromide, is ionic salt, or at least exhibits properties of ionic salts. We would expect an alkyl bromide to be covalent, so carbon-bromine bond to be covalent, and that carbon is supposed to be sp3 hybridized carbon as shown on the left. So it would exhibit typical properties of covalent species, which means it would be probably a liquid of this size or at least low melting solid. But this is actually, it has appearance of a salt, and it is more consistent with ionic bond between carbon and bromine. And the reason for existence of ionic bond is that if bond is ionic, then carbon is carbocation, and then cycloheptatriennyl ring is aromatic. On the right, you have molecular orbitals of cycloheptatriennyl cation, and you can see that just like benzene, 3 of the bonding pi orbitals are all filled. We have now 4 antibonding, they are empty, and again large HOMO-LUMO gap, so very stable species. This would be a valence bond description, so cycloheptatriennyl cation can be represented as a species that has 7 equivalent resonance structures, and positive charge is delocalized over 7 carbon atoms of the ring. Of course, not every species is aromatic or anti-aromatic. Some cyclic systems don't exhibit electron delocalization of that type. So some cyclic systems don't have closed loop of delocalized pi electrons, and then they are neither aromatic nor anti-aromatic. They may exhibit limited delocalization of maybe 2 double bonds or 3, but not closed loop of delocalized pi electrons. And then, of course, they can be neither aromatic nor anti-aromatic. Usually that will be the case if an sp3 carbon atom is present. sp3 carbon atom cannot be delocalized, and that will prevent formation of delocalized loop of pi electrons. Keep in mind that it has to be sp3 hybridized carbon atom. It cannot be one of those atoms that has free electron pair, like oxygen or nitrogen. Oxygen or nitrogen, at first glance, you may assume is sp3 hybridized. But actually, in situations like this, they would simply rehybridize, as you will see in a minute. Remember that hybridization is only a mathematical operation. This is not actual natural phenomenon. It's mathematical operation we came up with to fix broken theory, to fix valence bond theory. So if there is free electron pair present, simply that we assume that that orbital is rehybridized into atomic p orbital, and atom goes from being sp3 to sp2 hybridized, and we have closed loop of pi electrons. Finally, note example of fulvene. Fulvene, last one on the right, is not aromatic. That's because this carbon-carbon pi bond that is outside the ring is not part of the closed loop of pi electrons. It's not part of the ring of pi electrons. That one goes out of the ring. So fulvene and molecules like that, where only one carbon of the double bond is part of the ring, are not aromatic. Both carbons of the double bond have to be part of the ring to have closed loop of pi electrons. Of course, heterocyclic compounds could be aromatic. Heterocyclic compounds, just to remind you, are molecules that have atom in a ring that is other than carbon, heteroatom. So some examples are shown here. These are the most commonly encountered examples: pyrrole, furan, thiophene, pyridine. So when we look at 5-membered rings, they have 2 double bonds and a heteroatom, nitrogen, oxygen, or sulfur, and that heteroatom has 1 or 2 free electron pairs. Keep in mind that only 1 free electron pair, maximum of 1, no more than 1, can be in unhybridized atomic p orbital. And only electrons in p and pi orbitals could be delocalized. So any free electron pair that is in hybrid orbital, for example sp2 orbital, cannot be delocalized. So they don't count. When we count electrons to see whether molecule or ion follows Hückel rule, we don't count free electron pairs in hybrid orbitals, sp, sp2, sp3. So in this case, on each atom, nitrogen, oxygen, or sulfur of pyrrole, furan, and thiophene, only 1 free electron pair counts. The other one does not. In case of pyridine, there is free electron pair, but it doesn't count. That's because pyridine is already sp2 hybridized, because it forms 1 pi bond. Since pyridine forms pi bond with carbon, so carbon-nitrogen double bond, then free electron pair has to be in hybrid sp2 orbital. If it's in hybrid sp2 orbital, it's not delocalized and it doesn't count. So we only count 3 of the pi bonds, and so each of those 4 molecules is aromatic because they satisfy Hückel rule for 4n plus 2 equals 6 or n equals 1. Some more complex molecules, for example, one with 2 nitrogens, first one on the left in this second example, is also aromatic, and again, each electron pair on nitrogen does not count because each nitrogen atom is already sp2 hybridized because it forms carbon-nitrogen double bond. In the next example, middle one is isoquinoline. Again, 3 electron pair on nitrogen does not count, so there are a total of 10 pi electrons. In the last example, actually one of the 3 electron pairs on oxygen does count, the other one does not. One counts because oxygen does not form a double bond. So it is sp2 hybridized. One free electron pair is in hybrid sp2 orbital, while the other one is in unhybridized atomic p orbital. So that one counts. So all of these are aromatic. Now, how do you know in these examples, for example, oxygen atoms, nitrogen, sulfur, whether heteroatom is sp2 hybridized or sp3 hybridized? Well, you don't know in advance. So for resonance or electron delocalization in these systems, let's look at this example. One electron pair has to be in atomic p orbital. In sp3 hybridized oxygen, there would be no atomic p orbital, and that would not be possible. So what we do is we rehybridize atom and convert it from being sp3 to sp2. Ordinarily, if you were to see this molecule furan for the first time, you would reasonably assume that oxygen was sp3 hybridized. But that would not allow for electron delocalization. So what we do is we rehybridize it in such a way that makes electron delocalization possible, as shown here. So oxygen atom is represented as being sp2 hybridized. There is one localized electron pair in hybridized sp2 orbital, and the localized free electron pair is in unhybridized p orbital. So that one participates in delocalization. This completes our study of aromaticity and aromatic compounds, and next we are going to look at nomenclature of substituted benzenes.